So let's look at section B, and we start with the question 15, which has got 11 marks. And we start with the A, where we are told on the axis provided, sketch a graph of capacitance against the area of overlap of the plates on a parallel plate capacitor. And here we would like to remember that the capacitance of a capacitor, I would like to remember that the capacitance of a parallel plate capacitor is given by permittivity of free space, epsilon naught, area of overlap, divided by the separation between the plates. So you can see that the capacitance is directly proportional to the area and inversely proportional to the distance. We've been asked to state how the capacitance depends on area of overlap, and definitely it will be a straight line through the origin, because a straight line through the origin shows that the physical quantity on the y-axis is directly proportional to this one here, the one on the x-axis. So that one was just as simple as that. Part 2, we are asked to draw a circuit diagram that may be used to investigate the discharge process of a capacitor. Now, the process of discharging a capacitor cannot be isolated from the process of charging it. So, I've shown both circuits whereby when this toggle switch is on this side, then it enables us to record the current and the voltage during the charging process. And when it is fully charged, the voltage will remain constant, or the reading here will remain constant, and this one will show 0. So this one will be a maximum, this one will show 0. That is when it is fully charged. Now to discharge it, I'm going to move this toggle switch to the other side. So this circuit here that I've drawn in green is the one which was expected. But like I've put it, we cannot divorce the charging process from the discharge process, because the moment you touch a charged capacitor, it immediately discharges. So it's just important to connect or to investigate the charging and the discharge simultaneously. So the moment we connect this toggle switch on this other side, the capacitor starts discharging across the resistor. So there must be a resistor here for us to be able to observe how the voltage changes with time, and again how the current changes with time. That resistor is important. So that is the kind of circuit that we would expect. And then we are expected to draw on the axis provided, sketch the graph of potential difference between the plates against the time for the discharging process. Of course, it's going to be exponential. The voltage is going to decay out like that. That's what was expected. Now let's look at part C, where we are given this network of capacitors, and we are expected to determine the effective capacitance in the circuit. So the first thing we notice that this one is a series parallel connection of capacitors. When you are given this, we usually identify the kind of capacitors which we can easily combine. In this case, it is this capacitor and this capacitance. And remember, when capacitors are in parallel, we simply add their capacitance. For example, I can combine this and this to get a capacitance of 5 microfarads. And then now I've got 2 capacitors which are in series. At this point, because it's just 2 capacitors which are in series, I simply need to get the total capacitance, CT, will be equal to the product of the 2, which is 4 times 5, which gives me 20, divided by the sum, which is 9. And this will be 2 and 2 over 9, or 2.22 microfarads. That is what I get here as the total capacitance, or the effective capacitance. Now I can use that total capacitance to calculate the total charge which is stored. So Q is equals to CV. If it is total charge I want, I must get the total capacitance, which I know, times the total voltage from the battery. And that one is very easy to get because, let me just do it here. The total capacitance is 9/20. Let me just use 20/9 microfarads times 6 volts. I can convert this into farads, in which case I'm going to get this one in coulombs, but I can leave it in terms of microfarads, in which case now I'm going to get my answer in terms of microcoulombs. So I prefer to do this. Divide by 3, I get 3, divide by 3, I get 2, and that is going to give me 40/3. This one will go in here 1 because of 3, and then 3 goes into 10, 3 times and a third, or 13.33 recurring microcoulombs. So that is the total charge stored in the circuit. Now you'll realize that this total charge is the same charge which is stored across the 4 microfarad capacitor. Same charge. But when it comes here, the charge is split. Simply because current splits, then charge is going to be split. But this one, because it is in series with this one here, the charge stored here is equals to the charge stored in the 5 microfarad capacitor. While the charge stored in the 5 microfarad capacitor is the sum of the charge stored in the 2 microfarad capacitor and the 3 microfarad capacitor. So over here, since I want now the voltage, I'm in part 3 now. I want the voltage stored, or the potential difference across the 4 microfarad capacitor. When I use this equation, V is going to be equal to charge over C. The charge stored there is 13.3 microcoulombs, divided by the capacitance, which is 4 microfarads. Let me see what that gives me. That will be 13.3. We divide by 4, and we find it is 3.325 volts. 3.325 volts. That will be the voltage across the 4 microfarad capacitor. The rest of it is dropped across the 5 microfarad capacitor. And you can see that the larger the capacitance, the smaller will be the voltage. So the PD across the 5 microfarad capacitor, which is a combination of these two, is definitely going to be less than half of this value. But of course, very close to it. And that is how you would work out question 15. Let's go to question 16.